Okay, so in this lesson, I forgot to put it on here, so maybe I'll do that real quick. This is 1.7, the law of cosines. And our learning goal for this lesson is that students will understand how to use the law of cosines to model and solve real-world problems. So we probably need to know what the law of cosines is so we can apply it. Okay, so in your toolbox, I want you to put the law of cosines in here, and we're going to do it in two different forms. The first form is what we call standard form, and you can see that in standard form, one of the sides has been isolated. So we have a squared is equal to b squared plus c squared minus 2 times bc times the cosine of a. Now, of course, that's just one method of it. What if I didn't want side A? What if I wanted side B? Well, in that case, then we just have to rearrange the terms a little bit, and we'll get b squared is equal to a squared plus c squared minus 2ac times the cosine of b. Now, one of the things I want you to pay attention to here is the pattern. If I'm finding side a squared, then I'm going to be taking the cosine of a. And then if I'm finding side a squared, I'm going to be adding the squares of the other two sides, and then I'm going to be multiplying the cosine of A times 2 times each of those sides. Okay? So be looking for that pattern there so you can always recreate the law of cosines. The alternate form is what we're going to use when we want to solve for an angle because we've already isolated the cosine of A. And this just comes from taking this expression and solving for the cosine of A, right? We would subtract b squared plus c squared from both sides, divide by negative 2bc, and then simplify a little bit, and this is the form that we get. So for example, the cosine of A is equal to b squared plus c squared minus a squared divided by 2bc. So get down all of these in your toolbox, and then we're going to do two example problems. Okay. I just wanted to refresh your memory. This was on the lesson in the law of sines as well, but just to refresh your memory, we're going to use the law of sines anytime we have two angles and a side. So if we have angle, angle, side, or angle, side, angle, we use the law of sines. We're also going to use the law of sines if we have two sides and a non-included angle, right? And this is the case where you could have one, two, or maybe even no solutions. The law of cosines, a little mistake here, sorry about that. We're going to use the law of cosines if we know all three sides, or if we know two sides and the included angle. So two sides and the included angle might look like this. Two sides and then the angle that those two sides make. We did have a problem like that where we knew that information, but we were trying to find the area earlier in the law of sines, but we're going to, if we want to solve the triangle, we have to use the law of cosines if that's the information that we've been given. Okay. So example number one, let's solve the triangle given three sides. So we know three sides of the triangle. Let's say we know that those sides are 3 feet, 5 feet, and 7 feet. When we're trying to find, or when we're given three sides, we're going to use the alternate form of the law of cosines. And I want you to find the biggest angle first. Well, how do you know which angle is going to be the biggest? It's always across from the longest side. So 7 is the longest side. That means angle B is going to be the biggest angle. So we solve for angle B first. So write down the law of cosines. So we're going to solve for angle B. We use the alternate form. So cosine of B is equal to a squared plus c squared minus b squared divided by 2ac, right? Then all we have to do is plug in the values of those sides. So plugging in the value of those sides, we're going to get 5 squared plus 3 squared minus 7 squared all over 2 times 5 times 3. So working that out, we get 25 plus 9 minus 49 over 30, and that actually reduces to a real nice number, negative 1/2. Now remember, that's saying that the cosine of b is equal to negative 1/2. Oops, we'll take that away. So that means we have to do an inverse cosine. If the cosine of b is equal to negative 1/2, then b is equal to the inverse cosine of 1/2, which is actually a really nice angle, 120 degrees. So now I want to take that 120 degrees and put it in my picture. Here we go. Oh, and that looks like it makes sense. It's a nice big angle across from the biggest side. Once we know that, we could use the law of sines to find the other two angles, but I'm just going to walk you through the law of cosines again, and it doesn't matter which one you find next, so I'm going to find angle A. So here, the cosine of A is equal to b squared plus c squared minus a squared all over 2bc. And plugging in our values, that's going to give me 49 plus 9 minus 25 all over 42. So that means that the cosine of A is 33 over 42. So A is going to be the inverse cosine of 33 over 42, which is 38.2 degrees. So I'll take that, put my A in here. And then, of course, if I want to solve for angle C, I'm just going to add those two up and subtract from 180. And that gives me 21.8 degrees. So again, I'm going to label my triangle with all of these angles and just make sure that all of this makes sense. And it does. My shortest side is across from the smallest angle. My biggest side is across from the biggest angle. I know that I probably did this right. All right, in the next example, we're going to solve the triangle if we know side angle side. So let's say we know that side B is 12, side C is 9, and angle A is 121. So we're going to use the standard form of the law of cosines in this case. And we're going to start by finding the other missing side first. Okay? Now, I want to point out something to you guys. I want you to make sure that when you're starting with your standard form of the law of cosines like we have right here, make sure you're using the correct order of operations to do this. Okay? And what I mean by that is there's really like parentheses around here. You want to make sure that you find this product before you do any subtraction. Don't write this down, but what a lot of people do is they'll do 12 squared plus 9 squared, and then they'll subtract 2 times 12 times 9 from it. It's almost as if they have parentheses around here, and then they multiply by the cosine of 121. So please don't do that. Make sure you multiply all of this together first before you subtract it from the rest of the expression. So plugging in my sides, a squared is going to equal 12 squared plus 9 squared minus 2 times 12 times 9 times the cosine of 121. And right here, this is just calculator work, right? 12 squared is 144, 9 squared is 81, multiplying all that out. So when we get our expression, we get that value, we're going to get 336.248. But remember that that's a squared. A is going to be the square root of that value. So A is the square root of 336, which is 18.34. Perfect. So now I'm going to put that in my diagram and make sure it makes sense. Oh yeah, it's the biggest side, it's across from the biggest angle, it's about on the same scale as the other side, so that looks good. Now, once I have that side, I'm going to use the law of sines to find my other angle. So remember, sine B over B equals sine A over A. Plugging in my values, sine B over 12 is equal to sine of 121 over 18.34. I multiply both sides by 12 to isolate the sine of B. So now my 12's cancel, and I'll get the sine of B is equal to 12 times the sine of 121 over 18.34. That's just calculator work again. So B is going to be the inverse sine of that, which turns out to be 34.1 degrees. So now I have two angles. I can find the third angle by subtracting the sum of the other two from 180. So angle C would be 180 minus 121.34, or excuse me, 121 plus 34.1, and that gives me about 24.9 degrees. Let's check that back in my diagram. Oh yeah, that makes sense. If this was 24.1 degrees, that feels right. It's the smallest angle. It's across from the smallest side. All right, well that's all there is to the law of cosines. We'll practice some problems in class, and we will apply it to some harder problems.